Please tell your friends if they're not here, or be aware we have to sign this list just to know who is in the classroom, okay? So it's for every single lecture. So signing in the morning for Stariolo's lectures doesn't imply that you have signed for Stefanini's lecture 1 and Stefanini lecture 2, okay? So please, keep signing. So just to avoid misunderstanding, so I was appreciative and understanding of your need to have the Friday free, but because there are massive delays in the flights in the US and outside of the US, the final speaker may be coming with 1 day of delay or with massive delay. And so we had actually to do the opposite of what you wanted. We're going to have 2 lectures on Friday. I'm very sorry for that. We are trying to keep the morning free to at least make it mild. If someone was already scheduled to leave early on Friday, that's okay. Just come to what you can come to on Friday morning. Also, Paul Kofnikov will understand this exceptional situation. And so for that day, attendance is really flexible, okay? So don't get stressed about it. Good. With that said, so welcome again. It's my pleasure to introduce Martino and to chair his lectures. So Martino is the youngest of our speakers, maybe perhaps too young of our speaker. So in actuality, he graduated just a few years ago. And just to give you a few coordinates, he studied in Italy in premier institutions like Bologna and Scuola Normale Superiore di Pisa. He did his PhD in CISA working on low-dimensional quantum systems, and then I had the privilege and fortune to have him in my group. He's actually an expert on all strongly correlated systems in low dimension. We worked a lot on that, and in the process, we started to merge our backgrounds, and we came up with this review that Martino will be talking about. It's basically all misunderstandings or misinterpretation of Lindblad master equation. And feel free to ask questions. Martino is now at ICTP-SAIFR, and as I will say during my talk on Wednesday, he took the big bet to co-lead our satellite team here at ICTP. So thank you, Martino, for also replacing Hossein. That couldn't come for visa issues, and you have the floor.
Thank you, Jamil. So last week was very intense. We had a lot of field theory and strongly correlated stuff. I guess this week is starting a little bit easier. We've had classical mechanics before, which I always find, classical statistical mechanics, which I always find somehow reassuring. And also this set of lectures is going to be mostly on finite dimensional quantum systems, so nothing particularly fancy. It's a very well-known topic, but there are pitfalls and misunderstandings, and we gather them in a review that some of you already know. I'm not going to be showing really slides. This is just, as a title. And also because I wanted to put this as a pseudo quotation of Woody Allen, which ideally would have been another title for the review. But the review is this one. If you're curious, you find it on the archive. And so, just to gauge the audience who has never worked with open quantum systems. Okay, so who doesn't know what a density matrix is? Okay, you all know, perfect. So I can start faster. So also, and who has never seen the Lindblad master equation? Good. So the equation I'm talking about is this one. We have some system which is in contact with a larger environment. The system could be an atom, a group of atoms. The environment is usually very big and complex, might be the electromagnetic field, might be a bath of phonons in a solid, could be practically anything. And we are describing the system through its density matrix, which is a Hermitian positive semi-definite operator in the Hilbert space of the system. And under certain conditions, and which conditions have to be satisfied is the topic of the lectures. Under certain conditions, the dynamics of the density matrix of the system takes a special form, which takes the name of Lindblad form, or Gorini-Kosakowski-Sudarshan-Lindblad-Davies master equation, depending on your tastes. So this would correspond to unitary dynamics. This part here is called von Neumann equation. And this object describes dissipation. These operators are called jump operators. At this level, they can be any operator, could be unitary, non-unitary, Hermitian, non-Hermitian. And these are a set of positive rates, which are essentially decay rates for the processes that are described by each of these operators. So this is to, let's say, set the stage of what I'm going to be talking about. So in general, as I said, we want to describe these kind of systems. You can always, write down the full unitary dynamics of, let's say, the universe, system plus environment. This is generally, it can be done explicitly in a few cases, but this is not the rule, because, well, the Hilbert space of this thing is humongous. So there is, numerically is basically intractable, if not for the simpler cases, and we want to usually find a simplification for the dynamics. Now, on general grounds, one can put a few constraints on the kind of dynamics which is possible in a quantum system, in an open quantum system. Essentially, the dynamics is a map from density matrix to density matrix. And the map is generally of this form. You have an input state, which is initial state, and you apply the map, and you get the final dynamics. And this can be very general. Let's say this is a specific form of these dynamics. This function of density matrices cannot be arbitrary because, well, you input a density matrix and you want a density matrix at the end. So it has a few properties. The name of the properties is that it should be a CPT map, completely positive and trace preserving. So trace preserving is the simplest thing we want. So the density matrix must be normalized at each time. Essentially, its eigenvalues are probabilities, so they're positive numbers that sum to 1. And we want this to preserve these properties. Then, of course, we want that the density matrix is positive semi-definite, at each time, and this is the positive part. And then there's complete positivity, which is a somewhat technical constraint. If you imagine that there's a second system, which is an ancilla, and but which, let's say, you attach to the system, but doesn't have a dynamics on its own, then you want that the dynamics in the enlarged Hilbert space should stay positive. So even if, let's say, there's entanglement between these two parts, but let's say no dynamic on its own. But let's say the physical core of the CP3 conditions is essentially these ones. So, okay. In general, if you write down the full dynamics, it's unitary. These conditions are automatically satisfied, but the full dynamics is intractable, and also generally it has a property, let's say, in general it's non-divisible, which means that you may think of like evaluating this map at two different times. Might be certain time 1 and then time 2. And generally, the map that brings you from time one to time 2, so you just do the full evolution in 2 steps. So this map here is not a CPT map, so it's not a physical evolution. And this is called non-divisibility or non-Markovianity. And this is, for instance, not the case in the unitary dynamics, which we are accustomed to in closed systems. In unitary dynamics, this map is just unitary time evolution of a state, and this kind of dynamics is divisible. So if you can just have an evolution in many steps simply because this is true. But once you step outside of closed system, this property is no longer guaranteed for the dynamics. So in principle, you can only work with this object. But then one might ask, is it possible that actually this property of divisibility occurs in an open quantum system? And in the 70s, Gorini, Kosakowski, Sudarshan, and Lindblad proved that if you have a CPT map, so with these properties of keeping the state physical, and you impose divisibility, which is this. This is map composition. So if you impose this on top of CPT, then the equation must take this form. And in this sense, this if you have an equation in this form, the dynamics you will get by solving this equation is guaranteed to yield physical results. Of course, if you input a physical density matrix at the beginning. So this result made this equation very appealing for everyone that was trying to compute the dynamics of open quantum systems, because, of course, the fact that the solution of this equation is always going to be physical tells you that you can use this form as a phenomenological equation. So you know the kind of processes that are happening. Maybe the system is losing particle, maybe it's just heating up. And then you can just choose these operators accordingly. Let's say if the system is losing particles, this L could be an annihilation operator. If it's dephasing, it could be a density, and so on and so forth. And you can mimic your favorite open quantum dynamics by just doing phenomenological choices, and then maybe you fit the rates to experiment. Of course, this is very flexible, but let's say in all of this, let's say derivation they presented you, which is very mathematical physics oriented, there is no clue of the physical condition in which this is true. And the physical conditions have been clarified by other authors, especially Davis. And indeed, it turns out that there are situations in which this equation is a good or excellent approximation to the real dynamics. But to get from the full unitary dynamics to this equation, you have to make approximations, of course. So, and also, if you follow a derivation, you will start with a full Hamiltonian, and you will get specific explicit expressions of the jump operators and the rate, and potentially modifications to the Hamiltonian that you get. So I will now present you the derivation of this, and with comments and example on the typical pitfalls where the approximations fail. Okay. So my starting point is the full unitary dynamics of system as bath, and there's some interaction. I will quantify the interaction with some coupling constant lambda. You can assume it's an energy. And in general, you can always write the interaction as a sum of this form, where the A operators act on the system and the B on the environment. You can easily convince yourself that this is the most general that you can write. Also, I'm going to assume that these operators are Hermitian. These, again, can be done without loss of generality. And the whole derivation hinges on the assumption that this interaction parameter is small in some sense. And I'm going to proceed with perturbation theory, essentially. Where, of course, this is a perturbation, and this is my unperturbed Hamiltonian. So we start with also, I'm going to make an assumption on the initial state, which this is the state of the full system plus bath. I'm going to assume that at time 0, the state is factorized. So I'm going to assume that there is no pre-existing entanglement between system and bath. It's a generally mild assumption. Let's say in practice, you could think that essentially you are doing a sort of quench in which at time 0 you turn on the interaction and then you let it evolve. So the dynamics of the full state is given by the von Neumann equation, and this is unitary dynamics. And so our first step, yes?
So when you're assuming that you don't have previous entanglement,
Yes.
are you also assuming that the coupling, the initial coupling between the system and the environment is weak enough for that condition to be satisfied, or not necessarily?
So if the coupling is initially, I mean, has been non-zero since the beginning of the universe, then of course this would be false. There is a sense in which if the so the whole thing that I'm going to present now is to say that essentially the correction to this object in the as powers of the perturbative coupling are not relevant for the dynamics. But if you're able to turn on and off the interaction with the environment, this is not a particularly bizarre assumption. Trivially, in quantum mechanics, we also have measurement that helps us with this. If you let's say you excite an atom, you can essentially assume that the initial state is just excited state times thermal state of the electromagnetic field, and then this follows naturally. So, our first goal is to obtain an equation that involves rho s alone, so to get rid of the environmental degrees of freedom. Now, we want to use perturbation theory, so we go to the interaction picture with respect to the Hamiltonian, the unperturbed Hamiltonian, so system plus bath. For now, I'm not going to distinguish notationally the two. I'm going to be working mostly in the interaction picture, so there's no problems with confusing the two. Of course, interaction picture has an important physical root. So we are assuming that essentially the imperturbed dynamics is the one dominating. So it's the one setting the major time scales, because we want to do dynamics, so we have to be careful about time scales. Now, the interaction being weak is going to act on slow time scales. So passing through to the interaction picture has the meaning of essentially removing the fast timescales from the unperturbed Hamiltonian and leaving only the slow timescales associated with the interaction, which are the ones that will cause dissipation and we are interested in. So now I'm gonna the idea is essentially to iterate this equation to second order, passing through the integral form. So this is just a rewriting. Now we can take the trace over the bath degrees of freedom, and yes, and if if you write explicitly this expression for hi, you will see that this term will become something like a shift in the Hamiltonian of the system, something like this. Interaction picture, of course. So this is basically a classical driving of the system, because this is just an external field. So this does not cause dissipation, which is the thing we are interested in. So you either keep it like that, or you put it inside of H naught, essentially. And I'm just going to forget about this. Or if you wish, you can always essentially assume that these operators have zero average in the initial state. So we are left with this piece here, which is not particularly handy. And now there comes the first approximation that we're going to do. Now, OK, I'm going to, by the way, there's a derivative here. So we have, and all this double commutator. I'm going to write fast here. So the main idea is that we're going to, you can always assume that the full density matrix has this form, so that that the interactions are modifying the state of the system, and we consider the state of the environment, the initial state of the environment, like this, and then there is a correlation part. So let's say the non-separable part, the entanglement part. You can actually, let's say, this is going to be hand waving. You can justify this very formally by using projectors on the space of density matrices, but the formalism is a little bit more involved. You can find it in books. It's called Nakajima's 20 equation. But let's say the physical intuition is that whatever the correlations that the form between the system and environment are, these correlations are going to be weak in the sense that they're going to depend on the coupling constants. They're going to be suppressed by powers of the coupling constant. Now, if you plug this object here, there's a lambda square in front. So this term is going to be leading, and this term is going to be order lambda to the fourth. So if the coupling is small enough, this object will not contribute to the dynamics. And then it is legitimate to perform the so-called Born approximation, which is usually written exactly like this. And then you can perform explicitly the trace, and so this is the Born master equation, which is already more convenient because it's, let's say, this state of the environment is fixed, or it's known, so you can actually perform the trace, and this is an equation that involves rho s alone. Now, there are two comments here. They're important. This substitution makes sense only inside of the integral. So there is this is not meant as a good approximation. If you solve the true dynamics and compute this object does not look like this. Is a very bad approximation to the actual state. But if you make this substitution here, by this argument, you're going to get that essentially the leading part of the dynamics is driven by the separable part of the state. So this is the statement of the Born approximation. And the entanglement between system and environment under this assumption of weak coupling, and we're going to see also fast dynamics of the bath. So under these assumptions, the dynamics is only driven by the separable part, and the entanglement does not have an effect. Also, second remark, rho s of t, let's say the fully interacting rho s of t, is appearing on both sides of the equation. This is a self-consistent equation. So this is not, I'm not just doing perturbation theory, I'm not expanding rho s in powers of lambda and then matching coefficients. That would be a terrible approximation because you would get that the matrix would diverge in time. So this is an important technical point. Do you all see if I write on these lateral blackboards? Bigger? Okay, sure. Now, I can substitute this form. And I get more explicit expression so that it is evident now that I can take the trace, and this is, let's say, this is known information because I know the dynamics of the bath, I know the initial state, I know the operators, and this is a correlation function of the bath. Whereas the explicit operatorial part is just happening in the Hilbert space of the system. Now, one thing that I left a little bit implicit here is that for simplicity, I'm going to assume that the initial state of the bath is a stationary state of the bath, so that if I turned off the interaction, the bath would not evolve in time. And this is why I can keep the initial state of the bath rather than a time-evolving state. So in this case, this correlation function just depends, it's some object that depends only on the difference of times. This is not an assumption that's necessary to this theory to work. It's a convenient one. But of course, you can take, if the initial state of the bath is not stationary, then you must keep a time here. But it's the unperturbed dynamics of the bath that matter. This is not like a mean field ansatz in which I have to solve for the bath and for the system. And if the bath is not stationary, then you just put a comma here, and you have to consider explicitly 2 times. But this form is easier for beginning at least. Now, why do I care about this form? Of course, I want to do further approximations, but this already contains an important information. So this is an integral differential equation. The rate of change of the density matrix depends on the history of the density matrix, not just the density matrix at the same time. And the amount of memory in this integral is quantified by the correlation functions in the bath. Now, correlation function of the bath is usually some decreasing function of time, of the time difference. Now, if you assume that there is a specific, there's a overall time scale that governs this decay, so essentially, when this argument is larger than this tau b, the function is essentially 0, then it means that this integral is just receives contributions from this time. So it's all concentrated around the upper edge. And you can start iterating. You can, let's say, make estimates of the size of this object. And you can also iterate to higher order. And if you do so, then you will see that, roughly speaking, as a really order of magnitude estimate, this is something like this. And if you compute higher order terms, they are going to be, yes, like this. So, of course, we want, so this is a weak coupling approximation. We would like this term to be bigger than the rest of the terms. And of course, if you look at this, you will see that the condition for the validity of this approximation is this one. So the coupling times the correlation time of the bath must be, is our true weak, is our true non-dimensional parameter for perturbation theory. Of course, you cannot do perturbation theory in a dimensionful parameter. So when I was saying, well, the coupling must be small in some sense, this is the sense in which it's small. By the way, if I'm using h bar equal 1, if you use SI units, of course, there's an h bar here. So this is the first condition of validity. This is essentially the condition of validity for this approximation and also the next one. And you can find, if you're curious, you can find these kind of estimates in the book by Quentin Augy, Greenberg, and Dupont-Roch, which is a very nice book. Yes. So this was the first step, the first mile of the road, Born approximation. Questions?
So you say that this time of the bath is, it has to be really slow compared to the time of the dynamics of whatever I'm analyzing with this equation.
No,
is
actually,
that
is the no. Okay, it's the opposite. This time must be the fastest time scale. So this tau b must be very small.
Yeah, of course, that makes more sense. Just like my cavity has to be bad, and the atoms have to be fast.
Yes, yes. I'm gonna comment about cavity if I have times later. Yes, if you look also this estimate. This estimate also tells you what is the time scale of the system, which is this one. Now this is a rate equation. You can write it right. This is, sorry, there's a minus here. So this is telling you this is rho s is exponentially. You can expect exponential decay to some stationary state, and if you look at this, then the relaxation time scale from this is tau b over the square of the small parameter. So when this is satisfied, then the relaxation timescale induced by dissipation is much bigger than the relaxation time, the intrinsic relaxation time of the bath. So this condition here is another way of, let's say, rephrasing this condition. More physical one, maybe. So the interaction is weak in the sense that its effects are happening on a much longer time scale than the bare time scale due to the system and the bath without interaction. And we are going to use repeatedly this that condition of weakness. Now, the second approximation that I'm going to do is the Markov approximation. So we have an integral differential equation, the Born-Master equation, which is down there. And now, I don't know if you ever solved that integral differential master equation. Is not exactly pleasant, not on the analytic side, and it's not it's not particularly friendly, not even for computers. So we would like something that's more local in time. So the rate of change depends only on the present state and not on the past. Can we do so? Yes. But we need a little bit more of information. Essentially, we need to know the exact dynamics of the operators that couples, of the system operator that couples to the bath. Now, there is a simple way of writing this. So, of course, this is the definition. Now, if you write this in a basis of eigenstates of the Hamiltonian, so these are the exact eigenstate of the Hamiltonian, you can substitute this and change a little bit the sum, but eventually you will find that the dynamics has this form. And this is going to be fun. Okay. So the omegas are the sets of Bohr frequencies, so the transition frequencies of the system. And any operator is going always to evolve like this. So it's essentially like doing a Fourier expansion of the operators. And these objects, which depend on the eigenstates and on the operator that you're considering, these are called eigenoperators. Let's say, in practice, if you are able to compute this, these eigenoperators are really simple to find. You just, group the various exponential that you find and read off the coefficients. These are the eigenoperators. Otherwise, you can also write them using projectors. These pi are the projectors on the various energy levels. So essentially, if there are no degeneracies in the system, the pi's are just the individual projectors over the eigenstates. If there are degeneracies, you must sum over all degenerate subspaces. But let's say the outcome is simple. This thing is just telling you that when you apply, so that the eigenoperator with a certain Bohr frequency omega is reducing the energy of the system by omega. And indeed, you can show that they have nice commutation rules with this system Hamiltonian. There's a minus here. This is, again, telling you that these eigenoperators are work similarly to annihilation operators. And in case, I mean, depending on depending on the system at hand, this could actually be the ladder operators. Okay. So you can always decompose any operators in this. If you take t equals 0, then you have just a sum. Also, the dagger of this is just, let's say, is just acting in reverse. If this operator reduces the energy of the system by omega, this operator will have a plus here and is going to increase the energy. So these large parentheses, okay, it's just definitions and math, but this stuff is going to be relevant because these objects are going to be the ingredients for the jump operators. So if you want to know the jump operators, you need to know how these objects behave. Okay, I need to erase a little bit. So when I use that decomposition, times plus the Hermitian conjugate of all these things. So the structure with this sandwich term and the anticommutator is already forming, but that's a consequence of the nested commutators there. So this is just a rewriting of the Born master equation. Now, as I said before, we're assuming that this object is decaying fast. So this integral receives contribution essentially from this area for these times. Also, there is also this contribution here. If these frequencies, if all the frequencies are large, this will help essentially convergence of this integral. Again, if these times are differing more than the inverse of these frequencies, then this essentially will average to 0. Well, you can, I mean, it's an option. The point is, I'm not particularly interested in a specific form of the correlation function here. So I'm just saying it's some function that you can compute in the way that you prefer. But you can play the same game if that's your. So the alpha is because, I mean, they are, okay, I just erased, but the original interaction Hamiltonian is a sum. So let's say for each of these operators, which could be more than one, I decompose each one of these into eigenoperators. So these eigenoperators will keep memory of this alpha. Oh yes, the alpha and beta are here. This is the correlation function of the B's. No. No, indeed, have I used alpha for the eigenstate somewhere? No, no. Here the eigenstate, these are the eigenstates of the system. I'm numbering them with n. Alpha is some index. It could be that you just have one product, which might be common. I don't know, like if you have a two-level system with an Hamiltonian, which is something like sigma z, then the alphas might be sigma x, sigma y, sigma z. So this alpha would be x, y, and z. I mean, for what I want to tell, basically the fact that here you have a sum instead of a simple product is irrelevant. You can, in your mind, you can forget about alpha and beta if you wish. That this will not change the outcome. This is more general, because in general you need more than one operator, but you can derive everything and have the same discussion with just one operator for most of the purposes. So now the approximation. With this intuition that these two terms essentially are forcing. Yes.
Yeah, sorry, I got a bit lost. So why do you have 4 exponentials? Because each of the i's brings you 1 a. Each of the a's brings you 1 exponential, but then you got this omega prime minus omega times t. So that where does that exponential comes from?
This is
the second one.
Okay, these are just this is just a rearrangement because here you have 2 times.
Yeah.
Right. And you just need to rearrange the exponentials so that, let's say, because these guys are playing different roles. There's this bit.
Yeah.
There's a bit which depends on the difference, and a bit which just depends on one time. And these 2 guys are playing different roles. But it's just a rearrangement.
Okay. Yeah, thank you.
Yes, no, maybe. Good. So these guys are essentially forcing that, are constraining the integration essentially to live around tau prime, and let's say the interval that's relevant is it's something that's order of tau b or 1 over omega prime. Whereas I said there that we expect rho s to decay on a time scale which is actually much bigger than this time scale, because either the bath is fast or the system is fast. It's perturbation theory. So the Markov approximation is pulling these rows out of the integrals, which simply means this. So I'm just evaluating them at the upper corner of the upper corner of the integral. And this equation that you get, which is now an ordinary differential equation, so much simpler to solve, it's known as the Redfield equation. I mean, it's a name, but you know, it's this name is gonna recur. Now you can essentially do this integral, because now in this part here, nothing depends on t prime anymore. And so you can write this. I'll never stay here. Plus emission conjugate, and these gammas are essentially Fourier transforms or Laplace transforms, depending on your taste, of the correlation functions of the path. So this is essentially a Laplace transform of the correlation function at the frequency of the system. So this is a system frequency, whereas this is a property of the path. This is already possibly starting to look more reasonable to work with. An extra approximation, which is pretty common, is to again invoke the fact that these guys are decaying pretty fast to just replace them with the asymptotic value. I'm not going to rewrite everything. So you just, I mean, these guys, if you take an example, you can easily convince yourself that if C of t decays sufficiently fast, then this integral is dominated by the values at small times and will converge to an asymptotic value. And this is, let's say, the full form of the Markovian approximation, so that you have just essentially a rate equation for the density matrix with just constant rates, which are these limits. Okay. So this is the Redfield equation, which is used a lot. In many areas. Actually, this was the first one to be derived, historically speaking. It has already most of the things that we like. It's an ordinary differential equation. We have a set of rates that we can compute given a model of the bath. We have these objects. We start to look like jump operators, and we can learn a lot of stuff by analyzing the behavior of these guys. One thing that is lacking is that this this operator, sorry, this master equation is not CPT. So if you give a physical input, it might not give you a physical output. And the thing, it's not hard to convince yourself that this thing is still trace preserving. So the trace is fixed. What is not preserved is the positivity. So in principle, this object could describe, you could get negative eigenvalues for the density matrix. Or even as in the case of, for instance, an harmonic oscillator in a bath of harmonic oscillators, this guy will give you divergence, so that the density matrix just blows up in time. And this is a very well-known problem of this. Yes?
So here, as you mentioned, you're breaking the positivity.
Yes.
So what is the step that's causing this? Is it the second order perturbation and higher orders will cancel out these unphysicalities had we kept them? Or where's the like disconnect?
It's not obvious to see. Presumably, you have no Markovian contributions that would save you in the exact dynamics. So Born and Markov, what they're doing is essentially you are attributing a disproportionate weight to some processes. So each of these jump operators is giving you a process. Like you jump from one eigenstates of the system to a different one, and you have paired processes which different with different pairs of operators that are involved, and let's say you can interpret it as loss of positivity in the sense that some of these processes come with an excessive weight. If you wish, the rates that you need to compute are the eigenvalues of this matrix. And so for a matrix to be definitely positive semi-definite, essentially the off-diagonal elements cannot be too big. They have to decrease with respect to the diagonal ones. And what is happening is that some of the off-diagonal elements are too big. There are ways of amending this which are essentially like trying to curb them a little bit. But yes, the step is presumably possibly Markov or even Born, but it's probably might be even system dependent. I couldn't find a universal answer to this question. We thought about this really hard as far as we could, but no, it's not obvious. So, before going to the last approximation, which is exactly the approximation that you need to make this equation physical, I'm going to comment on a lot of stuff that we can already tell about this system. Sorry, about this dynamics. So let's start with the properties of the eigenoperators, which are essentially the properties of what we will see being the jump operators. Okay. So just to give a little bit of concreteness, if you are able to diagonalize the system, Hamiltonian, and if the spectrum of the system is non-degenerate, so essentially you're going to have jump operators of this form. So as I said, this is, well, actually this is the opposite, but this projector is exactly the thing that the object that brings you from one eigenstate to the other, and it is weighted by the matrix element of the original operator in the eigenbasis of the Hamiltonian. And of course, if there are like selection rules, these are hidden here. So of course, you could have that one of these objects is actually 0 if there is a vanishing matrix element. So the first lesson out of this is that the objects that are embodying the dissipative processes, or if you wish, what will be the jump operators, they are not simply the A operators that we started with, the ones inside the interaction. They are these objects. So this is often like people use, when people are using Lindblad in a phenomenological fashion, you just say, oh, well, the coupling is, I don't know, sigma x times something, or well, then the jump operators might be sigma x. No, it's not. Depends on the Hamiltonian. And this is the second lesson. So these eigenoperators strongly depend on the energies and on the eigenvalues, on the eigenvectors of the Hamiltonian. And because they're essentially, projectors in the space of eigenvalues, which means also that, let's say, if you have derived a certain set of eigenoperators for a given Hamiltonian, now if you perturb the Hamiltonian, the eigenoperators will change.
So like
yeah.
these are all jump operators that go from one state to the other because it vanishes when you remain in the same state. But why can't I imagine a coupling to the system where like I remain in the state?
No, you can. There is, I mean, having the same state here and here is an option.
But wouldn't then the EM minus EN vanish?
Yes.
But then
Yes,
the coupling.
it's not forbidden.
But why is the coupling? Okay.
Huh? So if the A operator, the original A operator, has matrix element on individual states, so then some of his, you will find that there is a corresponding eigenoperators at zero frequency. So this frequency is all the possible, let's say, okay, I'll try to picture. So you have a certain set of eigenstates, of eigenenergies in your system, and this operator will have certain matrix elements, which are non-zero, and it will just tell you which of these states are going to be coupled via dissipation. And this eigenoperators is just a way of, a systematic way of accounting for these transitions. But of course, let's say, you can have zero energy transitions. But then, which is this, the corresponding eigenoperator, if this is zero, it's a constant of motion. So essentially, if A has non-zero matrix elements, and if, let's say, if omega equals 0 is a possible frequency, let's say possible transition frequency of the system, it means that your original A operator has some overlap with a constant of motion, which is possible. A trivial example, you have an Hamiltonian which is again sigma z, but then you take a coupling operator, which is, again, sigma z. This is trivially a constant of motion. I mean, this is a very trivial example because it's a very limited Hilbert space. But you can apply this machinery to this case, and you will just find dephasing, which means that this kind of interaction will keep the diagonal elements of the density matrix while erasing the off-diagonal elements. But I mean, it's a perfectly admissible situation.
Okay, thank
you. Which actually anticipates one of the points about these properties of eigenoperators, is that in general, so eigenoperators, given this property, are not Hermitian. So if you take the dagger, you must change the frequency. Of course, if the frequency is 0, so if zero energy transitions are mediated by this operator, then this is Hermitian. But this constraint is also telling you that if you have a Hermitian eigenoperator, is also conserved. And this is an important point because you can prove that if you have a jump operator, let's say I'm skipping ahead, but if your jump operator is Hermitian and it doesn't commute with the Hamiltonian, so let's say then, okay, you can write, no, I'm writing the usual way. Okay. So this is an example of a Lindblad master equation that you can write on a phenomenological basis. I'm using, of course, the fact that this squares to 1, so the anticommutator is trivial, if you wish. So this has a jump operator, which is sigma x, and sigma x and sigma z, of course, do not commute. Now, under these conditions, you can prove that this object will converge to the maximally mixed state, which is actually at infinite temperature. Now, if this were admissible, it means that there is a situation in which you connect your system to an environment, and the environment pumps energy up to infinite temperature in the system. So unless you have an infinite temperature reservoir, this is not going to happen. And what is happening is exactly that the shape of these jump operators is exactly such that this situation never occurs in practice. So if you derive this from an Hamiltonian, this situation does occur, but it's either an approximation for finite times, so this cannot be valid at all times, might be an effective dynamics that you start from the more fundamental Lindblad dynamics and then you make some further approximations, or it's a completely non-Hamiltonian evolution. For instance, this is the exact dynamics in case I was measuring the system of the state. Sorry, the state of the system. So if I were measuring the spin along x of a qubit, and I take the measurements and then I forget about the measurement results, so I take an average of the state, this is exactly the dynamics. And because measurements are Markovian by definition. You make a measurement and you get an outcome and the state resets. But again, this is not equivalent to putting your system in contact with a reservoir. A reservoir will never perform a measurement for you. Instead, the only thing that can happen, so either you expect that the jump operators are non-Hermitian, common example, sigma minus, so this is the jump operator that it's relevant for thermalization to 0 temperature, or the jump operator can be Hermitian, but it must be conserved, which is sigma z in this case. Now, if the jump operator is conserved, then you still get physically admissible dynamics in the sense that this will not drive the system to infinite temperature. Well, this commutes with the Hamiltonian. Conserved commutes with the Hamiltonian. If you solve this equation with this jump operator, you will find that in the eigenbases of the Hamiltonian, so up and down, you have the diagonal elements which are kept untouched, whereas the off-diagonal elements, so these are going to be some numbers and will not depend on time, whereas the diagonal elements will have some decay, and they will go to 0. So this is the only situation in which this is admissible, and physically, I mean, this thing, so the energy of this state just depends on the diagonal, because this is the up and down basis of the qubit. So the energy will remain constant, but just the off-diagonal elements will be erased. And you get essentially a classical state. Maybe we can have, I don't know, present you maybe a few example of this to give you an idea of what is happening before doing more stuff. Well, I have like 15 minutes. Maybe I can give you a couple of examples if you're not too much familiar with this stuff. So, very common example, the decay of a two-level atom. So we have a two-level system, which might be an atom, and this is the ground state and the first excited. And there is, of course, a reservoir, which for atoms is the electromagnetic field, but it could be some two-level system in a solid, and the bath is, I don't know, phonons or spin waves or you name it. But the point is, the bath is, to a good approximation, often approximated by a set of harmonic oscillators. So in the sense that if the coupling of the system to a bath is weak enough, the bath will be just slightly perturbed by its equilibrium, from its equilibrium configuration, and you can essentially think of it in linear response theory, and small oscillations of something are harmonic oscillators. Now, of course, let's say this in the spin notation will be this, or 0 and 1. Use the notation that you prefer. So this is the Hamiltonian of the system. Then we have the environment, which is an infinite set of harmonic oscillators. And then we have some interaction. And I'm going to choose this form of the interaction. For those of you that are more familiar with quantum optics, this is the dipole coupling. It's the dipole times the electromagnetic field evaluated at the place of the atom. Of course, this is for sufficiently long wavelength photons so that the atom just see the local. So the structure of the atom is not resolved. So this is essentially the spin boson model, in case anyone might be familiar with that. And you can do a ton of stuff with this model. And depending on the properties of the system and the bath and the strength of the coupling, you can have a huge variety of behaviors. So, okay, let me put in practice what I said until now. So, what are the eigen operators of this system? So this is, for instance, a system in which there is just one A operator, which is sigma x, and one B operator, which is this displacement operator. As I said there, in this case, the simplest thing is to compute the dynamics of the coupling operator and read out the eigenoperators. So if you do so, you can easily find this. So there is only one frequency, of course, of the system is the splitting. So we have two transition frequencies, and let's say the plus omega is sigma minus, and minus is sigma plus. Okay. Now, if you work out this object, actually this is quite simplified in the sense that essentially here you basically don't need to do the rotative wave approximation, so this thing carries out exactly, and you will find so this is all that you get, and these gamma p and gamma pump and loss are essentially these big gammas evaluated, which depend on the correlation function of the bath. We can also have a look at the correlation functions here, but this is to give you an example. This term here, so to see the which kind of dissipative dynamics you have, you essentially need to look at these terms here. So that the one with in which the density matrix is sandwiched between the jump operators. So rho, so for instance, this term here is a pump term. So this sigma plus acting on a state is tending to excite the state from the ground to the excited, and vice versa. This term here is draining energy from the system and projecting the system on the ground state. And if you do the calculation, and maybe we will do it later, you will find that these two have a specific ratio that depends on the temperature of the bath, so that if you solve this equation, you will find that rho goes to a Gibbs state. So you can anticipate that the dynamics will lead to thermalization. And maybe after lunch we can also have this computation made explicitly. It's not particularly hard. So if the initial state of the bath is thermal, then this will reflect on the shape of these coefficients, and you can see that the system will thermalize at the temperature of the bath. And this is a nice property that we would like to have from master equation. We don't want to violate thermodynamics, because this is essentially a rewriting of thermodynamics. We have a small subsystem that is part of a larger system with lots of degrees of freedom. And if you open Landau-Lifshitz number 5 at the beginning and look at the derivation of the Gibbs ensemble, which is this, you will find that this is exactly how it's done. You single out a small subsystem, which is weakly interacting with the larger system, and they're assuming maximization of entropy. You derive this form, but let's say this is this formalism provides you with a dynamics that will actually lead the system to a thermal state. And maybe later I will try to argue that the fact that I'm using these weird eigenoperators is the thing that allows thermalization. If you were to choose these operators randomly, you might not get thermalization, because the eigenoperators know the state of the system, know the spectrum of the system. Okay. I think there's no point in going much further here. So, I don't know, questions? Shock.
I do have a question. You were mentioning the rotating wave approximation. When are we interested to enforce it? Because I'm pretty sure, if I remember correctly, you enforced that in order to write your expression in Lindblad form, right? But
so I have not yet performed the rotating wave approximation. For a two-level system, essentially, it doesn't matter. You will always get the wrong terms here will cancel out immediately, because essentially these guys square to 0. So in this example, you can just take red field, and actually you're gonna get Lindblad. Rotating wave approximation is for the future, maybe tomorrow, the full one. But I'm gonna comment on that extensively. More? So I guess we can go and have lunch.